Differential calculus is a branch of calculus that deals with the study of rates of change and slopes of curves. It involves the analysis of functions and their derivatives, which describe the instantaneous rate of change of a function at a particular point. Differential calculus is used in many fields, including physics, engineering, economics, and finance, to model and analyze dynamic systems and processes. Some of the key concepts in differential calculus include limits, derivatives, differentiation rules, optimization, and related rates. We will cover the following topics in this video. Introduction. What is differential calculus? Why is it important? Historical background. Limits and continuity. Definition of a limit, types of limits, limit laws, continuous function. Derivatives and differentiation rules. Definition of a derivative, power rule, product rule, quotient rule, chain rule, implicit differentiation. Applications of derivatives. Local extrema and critical points, optimization problems. Related rates, linear approximation and differential. What is differential calculus? Differential calculus is a branch of calculus that deals with the study of rates of change and slopes of curves. It involves the analysis of functions and their derivatives, which describe the instantaneous rate of change of a function at a particular point. Differential calculus is concerned with finding the slope of a curve at a particular point, and with understanding how changes in the independent variable affect the value of the function. This branch of calculus is widely used in fields such as physics, engineering, economics, and finance, to model and analyze dynamic systems and processes. Some of the key concepts in differential calculus include limits, derivatives, differentiation rules, optimization, and related rates. Why is it important? Differential calculus is important because it provides a framework for understanding and modeling many natural and social phenomena. It allows us to study how quantities change over time and how they are related to one another. Differential calculus is used extensively in physics and engineering to model physical systems such as motion, heat transfer, and fluid flow. In economics and finance, differential calculus is used to model the behavior of markets, interest rates, and economic growth. In biology, it is used to model population growth, genetics, and physiological processes. Differential calculus is also important in optimization problems, where the goal is to find the optimal solution to a given problem, such as maximizing profits or minimizing costs. Overall, differential calculus is a fundamental tool for understanding and analyzing dynamic systems and processes. It has wide-ranging applications in field of science, engineering, and economics. Historical background. Differential calculus has a rich and fascinating historical background. Its development can be traced back to ancient times, when mathematicians and astronomers such as Archimedes and Hipparchus used geometric methods to study motion and change. However, the modern development of differential calculus can be credited to the work of Sir Isaac Newton and Gottfried Wilhelm Leibniz in the 17th century. Newton is often credited with the discovery of calculus, and he developed his own methods of calculus independently of Leibniz. Newton's main contribution to calculus was the development of the concept of the derivative, which he used to study the motion of objects and the behavior of physical systems. He also developed the concept of the integral, which he used to calculate areas and volumes. Leibniz, on the other hand, developed his own independent methods of calculus, which were based on the concept of the infinitesimal. Leibniz's approach to calculus was more algebraic and symbolic than Newton's, and it emphasized the use of calculus in solving practical problems in physics, engineering, and economics. The rivalry between Newton and Leibniz over the discovery of calculus led to a bitter dispute between the two men and their supporters, which lasted for many years. However, both men made significant contributions to the development of calculus, and their work laid the foundation for the modern study of differential calculus. Today, differential calculus is a fundamental tool in many fields of science and engineering, and it continues to be an active area of research and development. Limits and continuity. Limits and continuity are fundamental concepts in differential calculus. The concept of a limit is used to describe the behavior of a function as the input variable approaches a particular value. Continuity, on the other hand, is a property of a function that describes how it behaves around a particular point. A limit is the value that a function approaches as the input variable approaches a particular value. It is denoted by the symbol lim and is written in the form lim f(x) equals L x a. Here, a is the value that x is approaching, and L is the limit of f(x) as x approaches a. The limit exists if the function approaches a single value as x approaches a from both the left and right sides. If the limit does not exist, it means that the function either approaches different values from the left and right sides or that it approaches infinity or negative infinity. Continuity is a property of a function that describes how it behaves around a particular point. A function is continuous at a point if its limit exists at that point and is equal to the value of the function at that point. In other words, the function can be drawn without lifting the pen from the paper at that point. If the limit does not exist or is not equal to the value of the function at that point, the function is said to be discontinuous at that point. There are different types of discontinuities, including removable, jump, and infinite discontinuities. A removable discontinuity occurs when there is a hole in the graph of the function at a particular point. A jump discontinuity occurs when the function jumps from one value to another at a particular point. An infinite discontinuity occurs when the function approaches positive or negative infinity at a particular point. The concepts of limits and continuity are important in differential calculus because they provide the foundation for the study of derivatives, which describe the instantaneous rate of change of a function at a particular point. By understanding limits and continuity, we can determine if a function is differentiable at a particular point and can use the technique of differential calculus to study the behavior of the function.